Hello, everybody, and welcome back to episode 48 of the video series in which we program an entire video game from scratch in the C programming language. So, hope everybody got their Xboxes pre ordered and their RTX 3090s pre ordered, and now you're ready to do some C programming. So, before we start, I only got one comment since last time, so let's go ahead and read it. Commenter says, using MSys2 with GCC is a great balance between needing Windows native build environment and using terminal/makefiles to compile. So let's go look it up. I've never heard of it before. I've never heard of MSys2. Is a collection of tools and libraries providing you with an easy-to-use environment for building, installing, and running native Windows software. Okay, so this is actually something that I will probably consider in the future because the more the further I go with this channel and this video series, I start getting a little bit tired, a little bit more and more weary of Visual Studio, and I'm starting to wonder if there's something better out there. That said, I'm not really looking forward to having to learn a whole new tool, and I also don't want to learn a new tool while I'm recording video either. But maybe that's just what we do. Anyway, so all right, let's see, where were we? So if you recall from last time, what we did last time is we added a brightness adjustment to a couple of functions here, both blit32 BPP bitmap to buffer, and also the blit background to buffer function. We added a brightness adjustment feature to those functions so that we could actually dim and brighten pixels at our leisure, basically, whenever we want to. If you supply a brightness adjustment of 0, then nothing will happen. If you supply a negative number, it will darken each pixel as it goes, and if you supply a positive number, it will add to the intensity. It'll brighten the color. Later on, I may want to break that up into colored channels so that you can control the colors individually. But as for right now, I'm just having it a single brightness adjustment color. So you can basically make all of the I'm using it now for the fade effects. Whenever I want to have the game fade in and fade out, I want to be able to do that with the bitmaps too, because having a fade effect is really important to me because it basically is an easy way to show like the passage of time. But here's the downside is we paid for this pretty heavily. This cost us a lot, and what do I mean by that? I'll show you. If you look at our frames per second now, they've gone down pretty significantly. I'm looking at this is staying at almost 500 frames per second, which is actually better than what I was looking at before. I had seen it go down to as low as 300 frames per second. And again, it's not always easy to measure because I've got this variable frequency CPU, and I don't know what frequency my CPU is at any given second. But anyway, the bottom line is that our FPS used to be much higher before we added the brightness adjustment feature, and now it's super low. So I would like to get that back up. Um, I would like to get our performance back a little bit. Um, there is a fine line between premature optimization. I don't want you to think that I'm necessarily going to be prematurely optimizing here, because there's a difference between premature optimization and correcting something that is egregiously wrong um, with performance. So when we were messing with this function, I think I'm going to focus just on this blit background to buffer function first. When we started working on this function, what we did was, it used to be just this right here. We had a bitmap octopixel because it is an AVX register. It's one of the YMM registers on the CPU that can hold 256 bits, and 256 bits is 8 of our pixels. So we're loading 8 pixels at a time from memory, and then we're basically going through every single color, every single pixel, one at a time, and we are adding the brightness adjustment to the pixel, but then we're clamping it. We're clamping the result between 0 and 255. The reason why is because, well, if it's not obvious, brightness adjustment, it needs is a 16-bit, is a signed 16-bit integer. And I think it needs to be a signed 16-bit integer because if it's not signed, if it's unsigned, then I can only have positive numbers in it, and then I wouldn't be able to darken the pixel because I can't take away color, um, and it needs to be 16-bit because if it were an 8-bit, a signed 8-bit integer can only go between negative. It can only go down to negative 127. So, for example, if I had a black pixel and I wanted to make it white, I would need to add a full 255 to it, um, and that would turn black to white, right? Now, if I had a white pixel and I wanted to make it black, I would have to subtract 255 from it. But a signed 8-bit integer is not big enough to hold negative 255. So that's why I settled on a 16-bit integer for this brightness adjustment value. I need something that's big enough to potentially hold up to negative 255. And then obviously with these 8-bit unsigned pixel values right here, where you are, it's very easy to overflow them and make them wrap around. If you had a black pixel that's 0 and you somehow accidentally added 256 to it, then you would wrap all the way back around to 0, and you wouldn't see any change, and you'd be like, how is it that I added 256 to this and it didn't brighten the pixel at all? And that would be the reason. So that's the point of me clamping. This is very common practice. You'll see this in lots of programs. Programs where the value needs to be clamped between some particular minimum and maximum. So I'm just clamping the value between 0 and 255. So if the result of this arithmetic is something like negative 60, then it's gonna get clamped to 0 because that's the darkest it can get. Um, it's also, I think you could also call this saturation, which is, we're going to run into that word again pretty soon, I think. Um, but here's the bottom line: is look at this code right here is garbage, and I know it's garbage. I admitted last time that it was garbage. Here is the general rule of thumb when it comes to SIMD, single instruction multiple data. Yes, you can access you can access these vectors, or these 256-bit registers or variables or data types, whatever you want to call them. Yeah, you can access them as a union. You can access them, different parts of them as a union. So what I'm talking about is, if I type in that and I hit that right there, you can see I can access the individual signed 16-bit numbers. There are six. It's just 16 of them. I can access the signed 32-bit integers, of which there are 8 of them. The 64-bit, which there are 4 of them. There are the signed 8-bit integers, which there are 32 of them. And then you can see the unsigned counterparts. I can also access those individually as well, just like as if just like a normal array. And you'll see this convention a lot too, where it says I16 and U16. That's simply, this one is signed, the I16 is signed, and the U16 is unsigned. So even though they do allow you to access parts of these 256-bit registers like that, I'm going to go ahead and say that as a general rule of thumb, if you find yourself doing that, you have missed the point of SIMD. So I would say if you find yourself writing code like this right here, you need to probably stop and reevaluate what you're doing, because you're probably missing the point of SIMD. See, the entire point of SIMD is to only have to call a single instruction and have that instruction operate on multiple pieces of data simultaneously. But here you see I'm tearing each little component apart and operating on each little piece of it individually. So that's like, I don't know a better way to put it than I've missed the point. So not only have I missed the point, but I've also really damaged my performance by doing this. And I think I can show you. I think I can show you if I set a breakpoint right there. And also, I want to make a shortcut too, so I don't have to keep going through the title screen. I think I'll make a shortcut for debugging purposes that takes us straight into the game, so that I don't have to go through the character naming screen and stuff. Okay, so we hit the breakpoint, and I want to look at all this disassembly. So I'm going to copy this, and I'm just going to copy the first 2. All right, can I copy? I don't know why it wouldn't let me. Why would it not let me copy this? Okay. I just hit Control C, and it does let you copy it. It just doesn't have the right click menu option for it. But anyway, look at this one line of code. This one line of code, the compiler turns it into 40 instructions. It takes 40 instructions to execute this one line of code, and that's just for this one color channel in this one pixel. So how many is that? If I have 40 CPU instructions, and then I do that 4 times for each pixel, and then I have 8 pixels, that's 1,280 CPU instructions that I potentially don't need. So we definitely need to make this situation better. I will go ahead and say this. I'm going to stop this. I'm going to switch this over to release mode. I will say that the situation does improve if we go to release mode, because at least the compiler is smart enough to optimize this to a degree. But if your code is really bad, there's only so much that the optimizer can do for you. All right, so here I've compiled in release mode, and let me make sure. Move. Yeah, see, there's a couple of I didn't expect to see. You can tell that we're moving something into this AVX register, and we're also using an XMM register, which is a 128-bit register. But on these subsequent, but you can see on like these subsequent ones, we do not do that. So I'm gonna copy like one of these. Go back here. Can I open a new view maybe? Clone, move to new view. There it is. Move to other view. Yeah, so we're essentially down to 9 instructions per color per pixel instead of 40. So release mode does make it a lot better, but we'll see if we can improve it even beyond that. Let me go ahead and pull this breakpoint, and we'll see what our FPS looks like. Pretty good. So the optimization from building in release mode still helps quite a bit. I feel like, and this is just an arbitrary decision. There is no right answer in terms of like how much frames per second is enough. But I feel like just arbitrarily for myself, if I can keep 1,000 frames per second, then I'm happy. Because this computer is pretty fast. It's like 3.5 gigahertz or something. But a lot of people, I mean, they are going to be playing this on much slower machines, and who knows? Maybe someday I may even want to port this to like a Raspberry Pi or something along those lines. So, and that's a much slower processor. So um, they won't be able to achieve nearly as high of a frame rate as I do on this PC. But anyway, as you can see, that's looking much better. But I'm still not going to let that be an excuse as to leave this junk here. Um, so what I'm going to do is this. I'm going to do an F0 precompiler directive, and oh wait, you know what? Actually, let me do indiff right here. Oh, indiff right here. I mean, and this essentially has the same effect as like commenting it out, right? There. So when I flip this between 0 and 1, I can either run the piece of code that'll be in here, in this block, or here. Like, this is the old stuff. Old and crusty. And then this will be where our new hot code is. So, okay, so here we are back to, I'm going to do F1 here. So now we're effectively back to having, like, this code is still going to run. We pick up 8 pixels right here with our octopixel, and then we skip all this and we go straight to store, and we store it straight into the back buffer, 8 pixels at a time. But we've lost our ability to do brightness adjustment. So how to fix this? Before I get started, I'm going to go ahead and make that shortcut that I was talking about, where if I go to if I go to opening splash screen.c, and let's see where to go. So essentially what I'm doing is I'm going to the splash screen, and I have to wait until the asset loading thread finishes, because I have to wait until all of my graphics are loaded first before I go trying to go straight to the overworld. All right, let's see if that works. Okay, it does. It works fine. Okay, so I think what we need to do, let's start by analyzing this octopixel thing. So let me. If I go to registers over here, you can see that I'm only displaying these basic registers here, but if I right click and go to AVX, actually I'll click SSE, this gets me the XMM registers that are 128 bits. I can also select AVX, and I get the YMM registers as well. And you can see that they're very long, they're 256 bits. So let me step one to populate. This is going to run, when I hit F10, it's going to run this line right here. And it did. And it populated YMM0 with that data right there. So let me copy that. And again, I can right click here and I can select copy. But if I select something over here and right click, suddenly there is no copy. It's one of those annoying things. I mean, it's like, on one hand, it's annoying. It's an annoying oversight on Visual Studio's part, but on the other hand, I'm worried that if I go to some other code editor, like, I'm not going to have the ability to do this at all. Like, I'm not going to be able to have the ability to look at these registers this way. So maybe it's an unfounded worry. I don't know. I haven't tried any other tools, so I don't really know. But anyway, okay, so there is my YMM register. Now, this will probably be X0 and Y0. Let me look at, yeah, X pixel and Y pixel are both 0. So this is most likely it's drawing, what is that? Temp folder. What is that? I don't know what that ENC underscore temp folder is. I've never seen that before. I didn't put it there. Anyway, doesn't matter. All right, if I go to maps, I go to overworld01.bmpx. Let's see what's at 0, 0. And this takes a while to load because it's like a 38 megabyte bitmap, right? Let's zoom in over here. Let's use the color picker to pick out this color. All right, so this first color is E000DC. So red is 224, green is 0, and blue is 220. So that is not this data. Not at all. Okay. Okay, now it is. Did it not? Did I selected something incorrectly? Was this not where what did I select the first time? Because I selected it again, and now all of a sudden it is the correct color. 5B, 6E, E1. I must have used the little color picker. I must have clicked on the wrong thing. Because yes, this is 00, and 00 in this bitmap will line up with what's in the code here, because we're in these nested for loops. We got an X pixel and a Y pixel. Um, yeah, so this is like alpha alpha, and then we have 5B, which is R. 5B, that's red. We have 6E, which is green, and then which just leaves blue, which must be E1. ARGB, ARGB. ARGB, ARGB, ARGB. That's 8 pixels. I would kind of like to do this on... Okay, so I kind of would like to do this for demonstration purposes. See, it's because this is 1, 2, 3, 4, 5, 6, 7, 8 pixels are all the same color. That's why our register it contains all one solid color right there. But for demonstration purposes, I kind of would like to get into where our group of 8 pixels contains multiple different colors. Maybe we'll do that. We'll do that later. So what I think I need to do now is, because these eight pixels, these 32 8-bit values are all packed in here, there isn't really much room to work with. And what I mean by that is, I still need to do arithmetic on these using a 16-bit brightness adjustment, right? Our brightness adjustment is still 16 bits. So I kind of feel like I need to get rid of these comments. I kind of feel like I need to break this apart, blow this register apart, and make it into 2 separate. Maybe I'll use 2 separate registers to hold half. So, like these 4 pixels right here, this is 4 pixels, and this is 4 pixels, and maybe I'll blow this apart into two different uh, registers. So essentially, we will have the same values, but each one of these color channels will now be 16 bits instead of 8 bits. So how to do that? First of all, you have got to become good friends with the Intel Intrinsics guide. So I know I've showed you this before, but it's an extremely important website. You should bookmark it. Basically, you filter by which family of SIMD you're working with. And right now we're working with AVX. Actually, we might be working with AVX or AVX2. I don't really remember. So I'll just select both of them. And so you go down and you look and you can see all of the intrinsics that applied that are for AVX and AVX2 operations. So these intrinsics apply to those YMM 256-bit registers. That is why most of these things, most of these intrinsics, they return these 256-bit values. That's why the function names start with MM256. And you also have the same syntax over here where you see EPI16. The I in I16 typically means that you're going to be dealing with signed 16-bit integers, and the P I think means packed. So if I click on this, it says compute the absolute value of packed signed 16-bit integers in A and store the unsigned results in destination. All right, so but we don't need the absolute value, so I'm going to go down to one of these is like a convert. One of these functions specifically converts 8-bit values into 16-bit values, and I think it's one of these. I think it's yeah, EPU. Yeah, this is exactly what we need. This says 0 extend packed unsigned 8-bit integers, which is what we have right now. We have a whole register full of packed 8-bit unsigned integers, and it converts them into packed 16-bit integers and store the results in destination, which is exactly what we need because we're going to have to do arithmetic on them with a signed 16-bit integer. So we do need to convert these. So I'm going to call this. So we need to declare a new MM256i, and I'm going to call it half one. And I'm going to use that function mm256 underscore CVT, stands for convert. And this is convert EP0048 unsigned 8-bit integers into signed 16-bit integers. And I need to give it, notice how this function takes a 128-bit input. So it basically needs half of this. It needs half of this 256-bit. So like the first half of my 256-bit register. And for that, I'm going to use another one of these functions. And it's mm256 extract something or other. Extract. Let's see, this is extract. This extract F probably means it interprets the results as floats. The PD, I think that means packed doubles and packed singles. So because a lot of a lot of people do their work using like floating point decimals, but we're doing everything in integers. So I want this extract I. extract I. So this says extract 128 bits composed of integer data from A, selected with IMM8, and store the results in destination. By the way, if I click on extract F, so this is, I believe, a typo, and I could probably email the whoever owns this document at Intel and say, hey, look, you got a typo here, because if I click on extract F128, it says extract 128 bits composed of integer data from A. I think this should say composed of float data or floating point data, because if I go down here to where it says, the one that says extract I, it also says extract 128 bits composed of integer data. So I think the differentiator there is supposed to be the one with the F in the name should be composed of floating point data, and this one should be composed of integer data. I think it's just a typo. Maybe I'm wrong, but I think it's a typo. Anyway, I want this function. Because what it's going to do is it's going to extract half. And like this is just your index. So if you supply a 0, it extracts the first half. And if you supply a 1, it extracts the back half, the second half. So I'm going to copy this. And then inside this function, I'm going to give it my bitmap octopixel, and then a 0. And then we're going to close that, semicolon. All right. Let's run that and see what the output looks like. Oh, I didn't realize the game was still running, but it is. So that's kind of cool. How I didn't have to restart the game. Okay, so let's look at our registers. So when I hit F10 again, I should run this line of code right here, the line that we just wrote. There it is. You can see now that the contents of YMM0 is that right there. So let me go ahead and stop this. Paste that in. Now I should have something like this: AA, RR, RR, GG, GG, blue, 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 blue. See that we basically took this first half of pixel data, these 4 pixels, and converted it so that now each color channel is 16 bits instead of 8 bits. So let me paste that in there. Okay, cool. And you know what? I can go ahead and copy that. I know I'm going to need a half 2 as well. So I'm going to run the same thing, but with an index of 1 should get me the other half of the 256 bits. Should give me the back 128 bits. Okay, now I think I'm ready to do arithmetic. And what I'm going to do is I'm going to do half 1 equals, and I need another. So if I go back to like how I was doing this before, how I was doing this previously, I was just doing the color plus brightness adjustment. So there's an intrinsic that's just like for adding, right? Yeah, see that you can add, and you can add different things like 8 bits, 16-bit at a time, all this kind of stuff. So, which is probably just what we want right there. So we're adding packed 16-bit integers in A and B and store the results in DST. And we want to make sure that we're interpreting these numbers as signed integers and not unsigned integers. So make sure, I don't even know if there is an EPU version of this, but if there is, you want to avoid it. because right now we're pretending like these integers are signed, right? So EPI 16, I'm pretty sure that's what we want. Okay, mm256 underscore add underscore EPI 16, and what are we going to add it to? Well, our first 256-bit thing is gonna be half one, right? And then what are we going to add to each of the components of half one? We're going to add our brightness adjustment, but our brightness adjustment has to be converted into an M256i, and that's pretty easy to do. There are intrinsics in here that are like for setting MM256 set. Yeah, here you go. So we can just set this with inputs. We can set it to here you go, set one. So if you have one signed short, which we do, a short 16-bit integer, we can basically take that and broadcast 16-bit integer A to all elements of destination. So I'll copy that. And it will be brightness adjustment. All right, perfect. So now what I'm doing is I'm adding brightness adjustment to each of those to each of these 16-bit components here simultaneously, and that right there, that's the key to SIMD. You know, single instruction, multiple data. Right. That's the whole key. Is if you are programming in such a way that you're issuing one instruction, and that instruction is having an effect on multiple pieces of data at a time, then that means that you're taking advantage of SIMD. So let's go ahead and run this and see what it looks like. Okay, there we go. Half one. Now after our addition operation, okay. After our addition operation, it looks like we have, go ahead and copy that. Kind of going off the rails here a little bit, I think, right? Because, okay, that makes sense to me because it was FF, and we just added, like, what is brightness adjustment? It's negative 255. So it was 255, we added negative 255 to it, and now it is 0. That's 16 bits, and the result is 0. That's fine. The next 16 bits is presumably, I presume that, I can't do the math in my head, but I presume that this is 5B minus FF results in this, and you can see that there's some sort of over, what do you call it? We've wrapped around, right? Because so this is some really high number. I'm curious to see what number it is. Sorry, make the text bigger. Yeah, so it's almost the max of that a 16-bit integer can have, and in fact, I think that is unsigned. I think if I convert this to, all right, negative 164. That's the answer right there. That's what it actually is, negative 164. In fact, and if I go over here to locals, and I go over here to half one, and I look at the signed 16-bit component, 164. 164. Yeah, there's my negative 164 right there. So, like I said, it's all a matter of how you choose to interpret the contents of this register, whether you want it to interpret it as signed 32-bit numbers or unsigned 8-bit numbers or signed 16-bit numbers, etc. Okay, so I think that arithmetic worked out just fine. But here's the problem is that I still have this issue where I need to clamp it, right? Because there's no such color like negative 164 is invalid. I mean, when I convert this back to 8-bit unsigned RGB values, it has to be between 0 and 255. So we still have this issue where we need to clamp, right? Which is also pretty easy to do. So let's go ahead and do that. So if I do half one, let me go ahead and stop the game. If I do half one equals 256 max. I can't type. EPI 16. We take in half one and then MM256 set 0 SI256 there. So this function right here is just a way to zero out, it gives us 256 bits worth of zeros. And what this function does is it basically goes through this 256-bit register 16 bits at a time, and for each 16 bits it compares them and says, is this greater or less than 0? And it takes the maximum value. So if the 16 bits is less than 0, then it gets converted to 0. If it's greater than 0, then it retains its original value. So we did that. Let's do the same thing, but with the maximum value. That covers the minimum value, which is 0, but we need to do the same thing with the maximum value, which is 255. So we're essentially taking these 16-bit integers and we're clamping them yet again between 0 and 255. So MM256 set 1 API 16 255. So what this is doing again is very similar. It's basically going through the register 16 bits at a time because of this right here. It's going through 16 bits at a time and comparing the value at that 16 bits. Hey, is this greater or less than 255? And over here, we've set this 256-bit register to all 255s in 16-bit chunks, right? Makes sense? And it's saying, look, if you are if you're greater than 255, then I'm going to take 255. If you're less than 255, then you'll retain your original value. So that we've clamped these values into sensible RGB color values between 0 and 255. So we're almost done. What we need to do is we need to repack this into a single 256-bit register again. We need to reassemble all these parts. So the first thing I want to do is I just want to repeat these steps for half 2. We'll do half 2. We'll do the same addition. We'll do the same clamping. see what time we're at. Yeah, we're at 50 minutes, so this is going to be cutting it close. Okay, so now we've done both halves independently. We need to recombine them. So there is a MM256 pack US EPI 16, and it takes in 256-bit vectors. So what this function does is specifically designed to take these two 256-bit registers that are composed of 16-bit signed integers, and then it's going to repack them, basically repack them into a single 256-bit register composed of packed 8-bit values. And let me look this up to make sure I got that right. I'm sure I did, but I want to make sure. Convert packed signed 16-bit integers from A and B, which is exactly what we have, back. This says two packed 8-bit integers using signed saturation, and store the results in D. So the one thing I noticed that's interesting about this is that there's a pack there. I think there's a pack. Pack S. The S stands for saturation, and I think because because this function automatically uses saturation, that means that the manual clamping that we did might actually be redundant. It may be actually unnecessary, and we can remove it. But for now, I'll leave it as is. What are we doing? Oh, right. So I'm going to assign bitmap octopixel. I'm going to assign the result of this operation to bitmap octopixel. So with that should be, I think that's about it. So let's run it. Let's take the breakpoint away. Okay. Now this looks like it sort of works, but sort of not. Oh, wow. That is really trippy. And I hope I'm not giving anyone a seizure right now, because that looks terrible. Something is definitely wrong here. So we on the plus side, our FPS is much higher. On the downside, we have completely gone wrong somewhere and screwed this up. Notice how everything, not only when I pan, it looks terrible. I don't know if it is coming through on your end. I don't know if you'll be able to see it in the video. But on my end, everything when I pan the camera, everything looks really jiggly and terrible, and like vomit-inducing. And furthermore, look at this portal. Look at the portal. It's like distorted some way. That's really weird. I'm gonna take a screenshot of that. Okay, so we've done something wrong. New. Okay, if you look at that portal, and then look at the original bitmap, see the difference? That's what it's supposed to look like, where it's just these concentric squares. But somehow our renderer has turned it into that. And I don't know what that is all about. So, right. Oh, actually, okay, actually I do. So if you go, and I think we already looked at the. All right, so if you look at Intel's documentation, it just says convert packed signed 16-bit integers from A and B to packed 8-bit integers using signed saturation, and store the results in destination. What it doesn't tell you, though, is what order it's going to return all these things in. So I'm pretty sure that's how we got into this state where everything looks really weird, is because our batches of pixels are in the wrong order. We reassembled them in the wrong order, right? So this function says, hey, I'll take your two 256-bit registers and reassemble them into one, but it doesn't tell us what order it does it in. That's why it's really important that you be able to read this pseudocode right here. If you notice, if you read the pseudocode really carefully, it's telling you that it doesn't return the results in the order that you think that they're in. It's actually something like, in fact, I'm going to go ahead and write it down. Okay, here we go. MM256 underscore PACUS EPI 16 A and B takes the 16-bit signed integers in the 256-bit vectors A and B and converts them to a 256-bit vector of 8-bit unsigned integers. The result contains the first 8 integers from A, followed by the first 8 integers from B, followed by the last 8 integers from A, followed by probably the last 8 of B, right? Last 8 integers from B. And here's the cool thing about the S for saturation. The S for saturation means values that are out of range are set to 0 or 255, which means we don't need these anymore. And reducing the number of instructions that we need is always a good thing. We don't need this. We don't need this. We basically just need to do our brightness adjustment, and that's it. We do that to each half, and then we recombine the halves. But there needs to be, I need to rearrange. The problem here is I need to rearrange these results. So how do we do that? I think what I'm going to do first is I'm going to make a new 256-bit vector, and I'm going to call it recombined. M256I recombined equals that. Okay. So I could do a couple things. I could just do bitmap octopixel dot M256I underscore U64, right? Because this is telling us that this pack US operation is going to return the results in basically 64-bit chunks, right? 8-bit integers. 8 times 8 is 64. So yeah, 64 bits. So I could do something like this. Equals recombined dot M260 There we go. And this will be 0, right? Because the result contains the first 8 from A, followed by the first 8 from B, which is going to be element 2 of recombined, followed by the last 8 from A, which is going to be element 1 in the recombined, and then finally there. Now let's see what that looks like. There we go. Perfect. Everything is looking good again. Scrolling looks good. Our portal looks good. We don't have these strange out of order pixels. And it looks like our frame rate is going to be around 1,000 FPS. Around 1,000. So that's pretty good. That's double what we were getting before, right? At the beginning of this episode, we were getting like maybe 500, 400 to 500, and now we're getting close to 1,000. So we've approximately doubled our FPS again, just by not using all this stuff. However, we're not quite done yet, even though we are out of time. But we're not quite done yet. And the reason why is because remember earlier on I told you, I literally just told you that if you find yourself accessing the individual members of this union, then you probably are doing it wrong. And I still believe that. So I'm actually not going to do that. I'm going to do the same thing, but in a more idiomatic SIMD sort of way. So let me comment that out. I'm going to shuffle this recombined variable. I could shuffle it without having to manipulate the individual members. So what if I do bitmap octopixel equals mm256. So there's a whole bunch of permutation functions in there. Permute, and it needs to be we're permuting in 64-bit chunks, right? 4 by 64, EPI 64. So for this function, essentially we need our input, which is going to be our recombined, our new recombined octopixel, 8-pixel thing, and then we need to supply a shuffle mask. It basically is a mask. It's a bit mask that is going to tell this function in what order would you like for me to shuffle these components. So I'm going to supply recombined here, and then I'm going to supply this mask, and I'll go ahead, the way to do it is with this shuffle guy, which is just a macro. As you can see, it's a simple, we're doing some shifting some bits around to give us our shuffle mask. And the order is going to be, it's going to be the same. See the 0, 2, 1, 3? It's going to be just like that, but in reverse order. So 3, 1, 2, and 0. And now we can get rid of these. And it should be good to go. I think that's it. So let's run it and see, make sure it still looks correct. There we go. And we still have close to 1,000 FPS, about 1,000 FPS. So, and that took a perfect amount of time, and we can we can eliminate all of this junk now. We don't need it anymore. I'm not going back to that. Let's take out this little if right here. Let's take out these maxes and mins because the saturation in this function already did the clamping for us, so we don't have to do any clamping ourselves. We got half one, half two, pack, permeate, store, done. And just one more time, let me look at it one more time to make sure that the fading, the effect of fading in from black is looking correct. Yeah, see how the world fades in from black? That's our brightness. That is the magic of our brightness adjustment. Okay, and that took just at an hour. So we can still improve. We can continue to improve this by taking this exact thing that we just did here and moving this to putting the same logic in blit 32 bits per pixel bitmap to buffer, which is probably what we'll do next time. It might be a little more difficult because not all bitmaps are guaranteed to be in multiples of 8 or 4. We might have a bitmap that is, has like odd dimensions, in which case we're going to have to compensate for that. So that's why I've been holding off on this one, because it's going to be more complicated. But I do think that there is a payoff to be had there, because remember the blit string to buffer also uses this function under the hood, right? So blit string would also inherently benefit from an improvement to blit 32 BPB bitmap to buffer as well. So I think we should go ahead and improve this function too, but we're out of time for today, so I'm going to call it. As always, thank you very much for watching. If you have any questions or comments about any episode, please don't hesitate to leave your questions or comments on the video, and I will address any interesting questions or comments in an upcoming episode. Also, if you enjoyed this episode and you enjoy watching the development of this video game, please hit the like button, please subscribe to the channel, please tell your friends. Lastly, don't forget that we have a GitHub repository that is companion material to go along with these videos, so you can clone the repository and follow along at home. So with all those things said, that is all for today. Thank you once again for watching, and I'll see you in a few days. Bye.